The first part of this sprint is concerned with a small algorithmic detail that is, however, of great importance. It is the difference between explicit and implicit phase coupling. What we mean by this will be clear if we follow the next couple of slides. Explicit coupling is a simple approach. If we consider that a drag force needs to be coupled between the DM and CFD part, other fluid particle interaction forces can be coupled in a similar manner, we understand as explicit phase coupling that the force itself is exchanged between the two parts of the solver. This can, as is immediately clear, be realized with a quite simple implementation strategy, i.e. only one field pair quantity needs to be transferred and the force is simply added to the right-hand side of the governing equation, which in this case is the momentum balance equation of the fluid. Also, because we couple the actual force values, explicit coupling can guarantee Newton's third law, which is actio et reactio, meaning that the coupling force on the particle must be exactly the opposite of the force on the fluid. This is an advantage of explicit coupling schemes, since no momentum is lost or generated in the coupling step. Unfortunately, explicit also means that the force data might be noisy, meaning that when the force is applied on the fluid side, for example, the fluid speed might rapidly change. We have already seen that fluid relaxation times are typically limiting and can be very small. Thus, explicit phase coupling requires small time steps, which is often suboptimal. Note that the above discussion for a drag force can also be transferred to multiphysics applications. In such applications, we do conceptually the same, e.g. when mapping a heat flux from the particles to the fluid grid. We now shift to an alternative that offers some advantages. This is so-called implicit phase coupling. Again, we look at the coupling of the drag force, which is a good example for a quantity that needs to be coupled. Implicit means that we want to use the fluid velocity at the new time for the drag force calculation when updating the fluid velocity field in the CFD solver. This means we cannot simply transfer the value of the drag force. Instead, we transfer a drag coefficient and a speed to the CFD part. In our case, the latter is the particle speed, as is clear when looking at the expression for the drag force. As illustrated here at the bottom right, the drag force at the new time n+1 is calculated with the new fluid velocity, but the current drag coefficient and the current particle speed. This way of calculation results into a more robust solver and can also be applied with a similar logic when updating the particle velocities on the DM side. Consequently, the implicit phase coupling algorithm requires a more involved implementation, i.e. two fields per quantity must be transferred. Also, Newton's third law will be conflicted when using an implicit coupling approach. The reason is that the particle solver and the fluid solver will experience a different drag force value for the same set of particles. Hence, the momentum during the coupling step is not conserved. However, there is a key advantage when using such an implicit algorithm. The time step on the fluid side no longer has to be smaller than the fluid relaxation time. This allows typically at least 10 times larger time steps to be used on the fluid side in case particles are small in the simulation. To round up our discussion, I also want to highlight a coupling approach that is a variant of the implicit coupling method discussed before, the implicit-explicit splitting. In this scheme, an explicit coupling force is split off the total coupling force before transferring the information for implicit coupling. This splitting uses a subtle difference between the per particle and the average particle velocity that is required in the implicit force updated on the CFD solver side. Implicit-explicit force splitting reduces the momentum error significantly, especially in dense flows. Results for a 2D jet in cross-flow setup, as well as the physical parameters used in such a simulation, are displayed on this slide. As can be seen, the implicit-explicit splitting coupling scheme allows for approximately 10 times larger time steps on the CFD side at a minimum momentum error. This is exactly what we want: fast simulations that respect the laws of physics as precisely as possible. In order to round up our unit on CFD-DEM coupling, I would like to close with a brief focus on the implementation strategies researchers have used to realize this coupling in simulation software. Specifically, two main strategies exist. The first one is a monolithic approach, i.e., the DEM and the CFD solver are implemented in the same tool. This typically means a complete re-implementation of either the DEM solver in an existing CFD tool or vice versa. An example is the toolbox OpenFOAM that is a well-established CFD solver. Relatively recently, a DEM solver was added to this toolbox, making it able to also perform coupled CFD-DEM simulations. The second strategy is to use separate solvers, i.e. a true coupling of software tools. Here we can differentiate two sub-strategies. Namely, the first one is to add an interface module that realizes the coupling on one side of the solver, which is typically the CFD solver. Examples include the tool CFD-DEM coupling, which allows coupling of the DEM solver lights with OpenFOAM, or AVL's ACCI code coupling interface that allows to couple a DEM solver to the AVL Fire CFD solver. Of course, a drawback is that the implementation in one solver is specific for this solver and it cannot be reused. Another sub-strategy is to use an universal coupling tool with multiple adapters. In the case of CFD-DEM coupling, this would mean an adapter for the CFD and the DEM solver that are then connected to the central coupling tool, for example the tool Precise. The layout of this beautiful tool is summarized on this slide. At the center of this figure there is the universal coupling tool that manages communication, maps the data, as well as realizing the coupling scheme and performs the time interpolation in case this is necessary. Each solver requires a dedicated adapter code shown here in green. The beautiful aspect is that also in-house solvers can be coupled relatively easily to a wide range of established solvers. However, there are currently also some drawbacks. For example, Precise is computationally not very efficient when it comes to a full so-called volume coupling, i.e. the whole field data is exchanged between solvers as is necessary for CFD-DEM coupling. The reason is that Precise is designed to couple data on two-dimensional boundaries only. Another disadvantage is that some mapping schemes currently will not work for volume mapping in Precise. Well, that was it. we now summarize the most important facts of our unit on the last 2 slides for today. First, this was the important topic on applications of the CFD-DEM coupling. I hope you see now that this coupling was invented because it was a door opener to many interesting applications for which no suitable solutions existed before. Also, the multiphysics aspect was a central part of this success, since many dense fluid particle flows are also connected to heat and mass transfer phenomena. When talking about the strategy and feasibility of CFD-DEM simulations, we first identified that there is a Stokes number sweet spot for CFD-DEM applications. Thus, our coupling method is not useful at the 2 extrema of the Stokes number portfolio. Simply, it would waste resources on the DM side in the very small Stokes number limit, or on the CFD side in the high Stokes number limit. Thus, there is a number of no-go applications which can be tackled much more efficiently with other simulation approaches. Once we have decided to perform a coupled simulation, we should also think about what exactly to couple. We've seen that there are essentially 3 different ways of coupling: 1, 2 and 4-way coupling. Another motto should be: think before you resolve. Most often, it will be enough to use an unresolved CFD-DEM coupling approach. However, as nicely illustrated in the work of Jäger et al., that was referenced in one of the slides, in some applications a resolved approach may yield more realistic results. We then have introduced some essential details on CFD and multiphysics aspects. Most important, we have seen that there exists one general transport equation that can be applied to many different physical quantities. We can use it for momentum, heat, species, and even droplet or fine particle transport. The governing equation for structure mechanics, in contrast, are a bit simpler when we compare this to this general transport equation. This is because there is no convective part, as solids do not flow. A notable exception is radiative energy transport. Here a diffusion-like continuum equation can be used, which was also detailed on one of the slides. Finally, we have talked about the details of coupling and seen that the permeability of the particle bed and hence the coupling strength is a central topic. Also, requirements related to the time and space resolution might be very different compared to single-phase fluid or particles-only simulations. Last but not least, it is worth mentioning that smoothing algorithms and implicit-explicit coupling approaches should be considered in case one wants to apply CFD-DEM coupled simulations. This was it for this unit. I hope you enjoyed the ride and are now well prepared for the quiz questions.